Monosaccharides such as glucose, galactose, and fructose form polysaccharides including maltose, lactose, sucrose, starch, and cellulose. These polysaccharides are connected together by a glycosidic bond. That glycosidic bond is an acetal. An acetal has an ether group bonded to the same carbon. An acetal is produced in a nucleophilic addition reaction of an aldehyde or ketone with an alcohol. In this reaction, a hemiacetal forms, which then reacts with a second alcohol to form an acetal. So stop the video and answer these 3 questions. Here are the answers. And see the next slide for the curved arrows. An acetal is formed when an aldehyde or ketone reacts with an acid, so stop the video and use curved arrows to show how each intermediate is formed. The first step is a proton transfer to form the conjugate acid. Note that the resin structure shows this carbonyl carbon to be a better electrophile. Here is the nucleophilic addition step when the lone pair and the oxygen reacts with the carbonyl carbon. And then there's a proton transfer step to form the hemiacetal. Once the hemiacetal forms, another proton transfer forms this compound. This group should look familiar. It's a good leaving group. And then a second alcohol will undergo nucleophilic addition to form the acetal. Glucose, a hemiacetal, is converted to glycogen and acetal. Insulin regulates our blood glucose levels. And pasta and oatmeal increase our glycogen levels. Carbohydrates form rings with a hemiacetal group, so stop the video and find the hemiacetal group. So here are the hemiacetal groups. So stop the video again and answer these 4 questions. We'll look at question 1 in just a second, but for question 2, the rings are diastereomers. The ring which is more stable is the beta-D glucopyranose, and the reason is because, remember, we looked at the chair form of a 6-sided ring, and the OH group is in the equatorial position in the beta form, whereas in the alpha form, the OH group is in the axial position. The anomeric carbon is the carbon which forms the hemiacetal group. And that carbon came from the carbonyl carbon. To form the 6-sided pyranose ring, this oxygen reacts with the carbonyl carbon to form the ring, and then proton transfer occurs to form the beta-D glucopyranose. This OH is the same as that OH in the chair form, and note that it's in the equatorial position, which makes it more stable. You may have used these reagents to test for reducing sugars in your biology class. Reducing sugars contain an aldehyde or ketone group in the chain or a hemiacetal group in a ring. Note that acetal groups in a ring, which are called glycosides, do not reduce oxidizing agents. So stop the video and draw the structure of this product. So here's the structure. Remember that an aldehyde is oxidized to an acid. A drug that contains an OH group is metabolized in our body by glucuronidation. Glucuronidation forms a glycoside. So stop the video and answer these 3 questions. So the answer is that this is the glycoside because this is the acetal in a ring. The reaction type is a substitution reaction. And UDP is used because this is a good leaving group. And remember that a leaving group is an important structural feature in a substitution reaction. This reaction is similar to the glucuronidation reaction in which an alcohol forms an ether. A cyclic acetal is also called a glycoside. So stop the video and answer these 3 questions. So the reaction type is a substitution reaction. To react the desired OH, an enzyme is needed. And remember that OH is a poor leaving group, so a better leaving group is needed for the substitution reaction. Ethers are underreactive, which is the reason they're used as solvents. If you want to do a synthesis which involves 2 functional groups, one of which is a carbonyl group at which you don't want the reaction to occur, you can convert the carbonyl group into an acetal, which serves as a protecting group. So consider this synthesis. We want to add one carbon to the alkyne, and we can do that by using the acetyl Now, to make the acetyl we can use a strong base, but a strong base reacts with a strong base is a nucleophile, so it can also react with the carbonyl carbon. So here's how we could accomplish that synthesis. Stop the video and draw the structures of compound A and compound B. So here are the structures. So compound A is the acetal. When the acetal reacts with NaNH2, the acetylide ion is formed. The acetylide ion is a strong nucleophile that reacts with methyl bromide in a substitution reaction to form compound B. And then compound B reacts with water to convert that back to the carbonyl compound. Remember that the nucleophilic addition reaction, as are many organic reactions, is reversible. A prodrug is an inactive drug which metabolizes into an active drug in our body. So let's see how fluosinonide is converted into an active drug in our body. Stop the video and answer these 3 questions. So here's the acetal. The conditions we need are acidic conditions, H3O+. And the other product is acetone.